In this video, we'll take a look at Newton's second law of motion. Newton's first law stated that objects at rest stay at rest unless the net force acts upon it. So Newton's first law tells us what happens to the motion of objects when all the forces cancel out or there are no forces acting on it at all. Newton's second law tells us what happens when there is a net force. When all the forces acting on the object fail to cancel out, there is something left over. And what it says is that when there is a net force applied to an object, it will accelerate in the direction of that net force. So again, Newton's first law tells us what happens to an object when there are no net forces. And what it says basically is the motion or lack thereof will be constant. Its motion will remain the same. When there is no net force, there is no acceleration. The object at rest will stay at rest. The object in motion will have a constant velocity. It will move in a straight line at a constant speed. The second law is telling us when you do have a net force, that object will accelerate. And it will accelerate in the direction of that net force. The second law is sometimes called the law of acceleration because that's what it's all about. Now recall, acceleration is rate of change in velocity. This is from our very first unit, where we're learning how to describe motion at its most basic level. Acceleration is rate of change in velocity. And velocity is speed and direction. So it's important that we understand what accelerate means. In most of our everyday life, when we hear the word acceleration, we think of an object that is speeding up. But that's not all of it. Because velocity is speed and direction. It's any change in speed, direction, or both. There are basically three things that can happen to an object when it accelerates, whenever a net force is applied to it. That object can speed up. This happens when the net force that's applied to the object is in the same direction as the object's motion. So if the object is moving to the right, and the net force is to the right, it'll speed up. If the object is moving down and the net force is down, the object will speed up. Again, the second law tells us when a net force is applied to an object, it'll accelerate in the direction of that net force. This is just making it a little more specific. If that net force is in the same direction as the object's motion, we will see that acceleration as a speeding up. Red arrows in the box indicate the direction that the object is moving. So if the object is moving to the right and the net force is to the right, this object would be speeding up. If the object is moving up and the net force is up, it'll be speeding up. If the object is moving to the left and the net force is to the left, the object will be speeding up. The second thing that an object can do when it accelerates is slowing down. Slowing down happens when the net force is applied in a direction opposite of motion. The net force opposes the motion of the object. If the net force is in the opposite direction of motion, if it opposes motion, the object will slow down. Again, red arrows in the box indicate direction of motion. If the object is moving to the right and the net force is to the left, the object would be slowing down. If the object is moving up, but the net force is down, the object will be slowing down. If the object is moving to the left and the net force is to the right, the object would be slowing down. Let's apply some real-world examples to both of these scenarios. This would be throwing a ball upward into the air. When you throw a ball up, it is moving up, but gravity would be pulling down on the ball. Gravity would be applying a net force that's opposite of motion, and it would be slowing that ball down. If I roll a ball to the left across the floor, that ball will immediately start slowing down because friction would be applying a net force opposite of motion, making that ball slow down. This would be something like a helicopter taking off. The blades of the helicopter, the engine of the helicopter would be applying an upward lift force as the helicopter is moving upward. If that lift is up while the helicopter moves up, it accelerates or speeds up as it takes off. This could be a car going down the road, where the engine is applying a forward net force, making the car speed up. So our first two possibilities deal with speed. If net force is in the same direction as the object's motion, it will speed up. If net force is in the opposite direction of the object's motion, it will slow down. The third possibility will be in any other direction. If the net force is applied in any other direction, then the object will change direction. The object would turn. So again, an object will speed up when the net force is in the same direction as the object's motion. It'll slow down when the net force is in the opposite direction of the object's motion. It'll turn or change direction if that net force is applied in any other way. So in this example, my object is moving to the right. The net force is being applied upward, so this object would turn upward. Because this force is perpendicular, there would be no change in speed as it did so. Again, to change the speed of the object, we have to be forward or backwards. This is directly perpendicular, so the object would just change direction. This object is moving upward while there's a net force being applied to the right. So this object is going to be accelerated in the direction of that net force. So it is going to turn to the right. This object is moving to the left while a net force is being applied downward, so it is going to accelerate downward. Again, applying this to everyday life, this would be what happens if you threw a ball in that direction. If you throw a ball in that direction, it doesn't go straight in that direction. It curves downward towards the ground. Because gravity will be applying a net force directly downward, causing that object to turn or curve towards the ground. This one over here could be a car that is traveling to the right. When you turn the steering wheels, it turns the tires in the car. And that generates a net force towards the center wherever you're turning. So if we turn the tires this way, it would apply a force in that direction, causing the car to turn in that direction. Looking at Newton's law, second law, the law of acceleration, tells us whenever a net force is applied to an object, it'll accelerate in the direction of that net force. If the direction of that net force is the same as the object's motion, it will speed up. If it's opposite of the object's motion, it will slow down. If it's any other direction, it'll cause it to turn. Objects can do more than one thing at a time. They could speed up and turn. They could slow down and turn. They'll never speed up and slow down at the same time. And that happens when there's some kind of angle to the force. And this goes back to what we did with net forces and how we learned how to break these angled vectors down into their two components. At this point, we know that when we have a force that points out in this direction, that there is going to be some x and y component to it. There's going to be some horizontal and vertical component to that motion. There will be a certain part of this that goes in this direction and a certain part of this that goes in this direction. And that's where we take this vector and we break it down into its two parts, and we calculated what the x and the y are. Anytime we see one of these angled vectors, we know there is some horizontal, there is some vertical component to this. So this particular vector will produce some portion of force that goes this way to the right and some portion that goes up. So we're going to see two things happening at the same time here. Because the object is moving to the right and we have a component of that force that is also to the right, this object would speed up. We also have this upward component to this vector, perpendicular to the motion. So this object will also turn. It'll turn upwards or north, or however you want to describe it. So this object would speed up as it did that. And again, that's just recognizing that any one of these angled vectors can be broken down into a specific x and y component. And each one will act independently. This x component will speed the object up. This y component will turn it in whatever direction it's facing. Same thing is going to happen over here. We have a vector that's going in this direction. And again, we recognize that this is broken down into two separate parts. There will be a certain part of this force that goes in that direction. And there will be a certain part of this force that goes in that direction. And again, it comes from the net force stuff we did. If I have that vector and I want to break it down into its x and y components, there's a certain part that's going to go down. There's a certain part that's going to go to the right. An x and y component to that particular vector. And these two things will act on that object independently. This object is moving to the left, and we have a part of this net force is acting in the opposite direction, so we know it's going to slow down. But at the same time, we have this downward component acting perpendicular to the object's motion that's going to cause it to change direction. So it is going to turn this way at the same time. So it's going to slow down as it turns downward. Again, they'll never speed up and slow down at the same time, but they can speed up and turn or slow down and turn whenever you have one of these angled vectors. This is a more realistic scenario as to what actually happens when you turn the steering wheel of a car. Car would be going in this direction, and then you would turn the wheels so that they're angled like so. What that'll do is slow the car down and turn it at the same time, because you actually get a more angled vector. There are two factors that affect the magnitude of the acceleration: how quickly it speeds up, how quickly it slows down, how quickly it turns. And they are the mass and the strength of the force that's being applied. Mass and force. Those are the two things that will affect how quickly the object will accelerate. How fast it speeds up, how fast it slows down, how fast it turns. Mass and acceleration are inversely proportional. Inversely proportional means they change in the opposite way. They are the inverse of one another. So if I have 2 times the mass, I will have the inverse of that, or 1/2, the acceleration. They're inversely proportional. What you do here, you do the inverse over here. So if I have 1/3 the mass, my acceleration will be the inverse of that, or 3 times the acceleration. Mass and acceleration are inversely proportional. Whatever you do to one, you do the inverse to the other. Just flip the number. 4 times the mass would be 1/4 the acceleration. 1/5 the mass would be 5 times the acceleration. Just flip it, take the inverse, and you've got it. Real world example of it, pushing on a car. You can get much higher acceleration pushing on a toy car than you can on a real car. And the explanation for that, the reason for that, is mass. You could apply the same force to both objects. That force, however, would be acting on a much smaller mass over here. And because that mass is lower, you'll get much greater acceleration. When that same force is applied to a much larger, much more massive object, that acceleration is going to decrease substantially. And again, if this car has 500 times the mass of that one, you would get 1/500th the acceleration, the inverse. Again, it's a mass-driven phenomenon. You're applying the same force to both cars. The toy car accelerates more because the toy car has less mass. Simple enough. The other factor that affects the acceleration of the object is the actual force that you apply. And force and acceleration are directly proportional. Directly proportional means they change in the same way. So if we apply 3 times the force, we would get 3 times the acceleration. They do the same thing. If we applied 1/2 the force, we'd get 1/2 the acceleration. Directly proportional means they'll change in the same way. Whatever you do to the force, you'll do the same thing to the acceleration. 100 times the force would be 100 times the acceleration. 1/10 of the force would be 1/10 the acceleration. Again, applying it to real-world objects, if we have 1 person pushing on a car versus 3 people pushing on a car, in theory, we could get about 3 times the force over here, and we would get about 3 times the acceleration. The more force you apply, the greater the acceleration is going to be. Those are the 2 factors that affect the acceleration of an object. Next week, you'll learn how to calculate this. You'll learn the actual equation for it, and you'll be crunching numbers and seeing exactly how these things work. Exactly what happens when you change mass is exactly what happens when you change the forces applied to an object. But for now, this is what you need to know. The next thing I want to talk about as it relates to Newton's second law is momentum. In the first law, I talked about inertia. the tendency in an object to resist changes in motion. Objects with high inertia resist changes in motion. So a massive boulder has a tremendous amount of inertia. It's hard to get it moving. Once that giant boulder is moving, it's hard to stop it because of all of its inertia. Momentum is very similar. It also tells us how difficult it is to change the motion of an object. It tells us how difficult it is to accelerate an object, to speed it up, to slow it down, to turn it. Key difference is that inertia applies to everything. All objects have inertia, whether they're moving or not. Momentum only applies to a moving object. Only moving objects have momentum. Inertia is only affected by the mass of the object. Something with a small mass has a small inertia. Something with a large mass has a large inertia. Momentum is affected by two factors. Because the object has to be moving, not only will the mass of the object affect its momentum, but how fast it's moving will affect its momentum. Again, very similar story. When something has a large inertia, it's difficult to speed it up, slow it down, or turn it. When something has a large momentum, it's difficult to speed it up, slow it down, or turn it. So you could use all the same examples that we did for inertia. A large pickup truck would have a lot more momentum than a small little two-door coupe would. A baseball would have less momentum than a bowling ball moving at the same speed. So the same kind of examples. But again, this object has to be moving. When an object is not moving, it has inertia, but it has no momentum. And again, that's because momentum is also going to be based on velocity. It still means the same thing. When we talked about inertia, one of the examples that I used in my video was trying to hit a bowling ball with a baseball bat. If you take a swing at a baseball, you can hit it, you can change its direction, you can send it flying towards the outfield. But if you took a bat and take a swing at a bowling ball, you're not going to change its direction. Probably just going to break the baseball bat. And the reason for that is it would require a larger force to make that bowling ball change direction. It would take a larger force to make that bowling ball go the other way. This is basically saying the same thing. That bowling ball is moving, it has high momentum. It would require a larger net force to change its motion, to slow it down and stop it, and then speed it up the other way. As I said a couple of times now, it's affected by two factors, mass and velocity. Inertia is only affected by mass because momentum applies to moving objects. The velocity is going to factor in there as well. This is also why something that's not moving has no momentum. If it's not moving, its velocity would be zero. And when you plug zero into its calculation, you get zero. Again, this is something that you'll be calculating next week. You'll learn how to use this equation, how to calculate an object's momentum and work with it. But for now, we're just keeping this on a basic level, understanding how these two things affect momentum. Mass and momentum are directly proportional. So as before, directly proportional means they change in the same way. So if you had 3 times the mass, you'd have 3 times the momentum. If you had 8 times the mass, you'd have 8 times the momentum. If you had half the mass, you'd have half the momentum. Mass and momentum are directly proportional. And one of the examples that I did talk about in the inertia part of the first law was the empty shopping cart versus the full one. Lower mass, higher mass. Lower momentum, higher momentum. If you get this thing whizzing down the aisle of the grocery store and get to the end, you can turn it real quick. No problem. But if you get this thing moving down the aisle real quick and you get to the end of the aisle, you really have to pull on it to slow it down. You really have to push hard on it to get it to turn. And that's because the extra mass it has would give it more momentum. This one, real easy to speed up, real easy to slow down, real easy to turn, because the mass is relatively low. This one, significantly more difficult to speed up, slow down, and turn because of the additional mass it has. Velocity and momentum are directly proportional. So again, they change in the same way. If you double the velocity, you would double the momentum. If you cut the velocity in half, you would cut the momentum in half. Whatever you do the velocity will also do the momentum, directly proportional. I can shoot a projectile with a slingshot or with a gun. And those projectiles could have the exact same mass. But the one shot from the gun will be much harder to stop. And the reason why it will be much harder to stop is because of its velocity. The velocity of the projectile coming out of the barrel of the gun is incredibly high. In some cases, we're talking about velocities of 1,400 or so feet per second. 1,400 feet per second is like a football field and a half every second. Very, very, very high velocities. And because of that extremely high velocity, it has an incredible amount of momentum. And because of all that momentum, it's really hard to stop. The slingshot is going to give you much lower velocity, and because of that, much lower momentum. This would do something like going through the wall of a building without much issue, whereas this one couldn't. And again, the difference is momentum. And what causes that difference in momentum is the velocity difference between the two. Another great example, this is why you slow down when you come up to a turn in the road. You slow down when you come to a turn in a road to reduce your momentum. If you cut your speed in half, you cut your momentum in half, and it makes it easier to turn the car. If you don't slow down for the curve and your momentum's too high, then the tires may not be able to apply a significant enough net force to make the car turn. And then the car goes straight off the road. Physics. So the best drivers are the ones that understand physics. They know what their car is going to do. They can predict how their car is going to behave before they do anything with it. Some of the best NASCAR drivers are engineers. They've gone to college to study engineering. They have a thorough understanding of physics. So they know exactly what their car is going to do when they ask it to do something. And there's going to be a lot of math with the second law. That's where all the equations come from in this particular unit, and we'll get to those equations next week. But for now, we want to be able to interpret the free body diagrams, be able to look at those free body diagrams and predict the future motion of an object. So we look at a situation like this, we want to figure out what the net force is, and we want to compare that net force to the actual motion of the object. Again, the red arrows that are in the boxes indicate the direction that the object is moving. So I would do my normal net force thing here. I look at my forces that are taking place in the horizontal. I have 6 newtons to the right. I have 4 and 2 newtons to the left. As you know, we can add these two together because they are in the same direction. So I have 6 newtons to the left, 6 newtons to the right. We know these forces are going to cancel out. They will balance each other out. I have 7 newtons up. I have 8 newtons down. These will not completely cancel. I know that's going to go away, and this is going to leave me with 1. So I have a 1 Newton force that is downward. while my object is moving to the right. Again, whenever we have a perpendicular force like this, it's going to cause a change in direction. This object will move at a constant speed. I can say that because there's no part of my net force that is either in the same direction or opposite of motion. There's no speeding up or slowing down going on. But I do see that I have a force that is perfectly perpendicular. This object is going to turn downward. So that's my prediction for the future motion of this object. It's using the free body diagram, finding the net force, and then using that net force and the object's motion to make some kind of prediction. Do remember we could do problems like this, those super complicated ones where we have to break down that 50-degree force into its x and y components, then put them all in the free body diagram to see what's going to happen, and use that to make some kind of prediction. Again, a single problem like this can take you 5-10 minutes to get through. I start with my angled force, and I want to figure out what the x and the y components are based on that 50-degree angle and the 25 Newton force. Y is opposite of 50, so I'll use sine to find the y. And it is sine of 50 times 25. So this is going to be 19 newtons. The x is my adjacent side. Again, adjacent is the one that's actually part of that angle. So it's cosine to find x. So cosine 50 times 25. This one, cosine 50 times 25 is 16. And when I've done that, now I can redraw my free body diagram without this in it. I'm just going to go ahead and get rid of this. That's gone now. I have an upward of 19. And I have one to the right of 16. Now, given that, I can reevaluate my forces, simplify all my forces. On this side, I have 11 newtons in this direction. Over here, I have 26. I will subtract those two, and I will end up with 15 to the right. And it doesn't matter if you do the horizontals first or the verticals first. You'll get the same answers and angles regardless. My upward is 19, my downward is 15. So I have an upward force, net force, upward of 4. And now I got to use Pythagorean theorem to find what my resultant is. Got to find that. Again, remember when you do these two here, put it in the wrong spot. Make sure that you connect them tip to tail. So I had my 15 this way, and then my 4 I attached to the tip of the arrow, not the end of it. Find my magnitude is Pythagorean theorem. A squared plus b squared equals c squared. So c squared is 241. Square root both sides. 15.5. Going all the way to finding the angle here, I'm going to use sine. Sine is opposite over hypotenuse. Opposite of this was 4. Hypotenuse is 15.5. 4 divided by 15.5 is 0.2580. 64561. It goes on. Then I'm going to take the inverse sine of that number. And my angle is 14.9 degrees. Let's call it 15 degrees. So 15 degrees. And I can leave this one 15 degrees because if I think about the unit circle, again, I know if I'm over here, that's 0. If I'm up here, that's 90. If I'm over here, that's 180. If I'm down here, that's 270. Increases by 90 every time. My angle at 15 degrees is there. So it's 15 degrees above 0, so 15 degrees would be the actual number that I would use. If you wanted to put a direction on that, that's north of east. All right, that's second law. Stay tuned for the third.